In much of this chapter, we've been talking about neutral acids, but we do want to take a minute to talk about cationic acids. Right? So what we mean by cationic acids is acids with a positive charge. So I'm thinking here about things like the ammonium ion. So how do we compare the acidity of compounds that have positive charges? Right, in previous videos, we've considered the relative strength of neutral acids. So if I wanted to know how strong an acid this carboxylic acid is, I would actually look at its conjugate base and see how well that conjugate base can stabilize the negative charge. Well, when we're looking at cationic acids, their bases are neutral. And so we're going to treat these a little bit differently because there's no negative charge on the conjugate base that we can use to determine the relative acidity of our cationic acid. Right, so if I'm trying to determine the relative strength of this neutral acid, I would use REO to look at how well this compound can stabilize the negative charge. Now for cationic acids, if I wanted to think about how strong this acid is, I'm not going to look at the conjugate base, but I'm going to apply REO to the acid itself. Right, for neutral acids, when we do this qualitatively, we're looking at the conjugate base. For cationic acids, we're going to apply REO to the acid itself, although we're not going to get into resonance and induction and orbitals. It can get kind of complicated for these cationic acids. We're just going to focus on A, the atom type. So what atom has the positive charge in our cationic acids? Right, so remember, for negative charges, they're more stabilized by elements with higher electronegativity. Right, things with high electronegativity want electrons, and so they're relatively happy with negative charges. Positive charges, on the other hand, are more stabilized by elements with lower electronegativity. And so remember that stable equals weak. And that doesn't matter whether we're talking about acids or bases, but the more stable the acid or base is, the weaker it is. So if I was given these two cationic acids and was asked which one was the stronger acid, I would look at how good is each element that has the positive charge, in this case the nitrogen, and in this case the oxygen, how good are nitrogen and oxygen at stabilizing positive charges? Well, positive charges are more stabilized by elements with lower electronegativity. We know oxygen is to the right of nitrogen in the periodic table, so oxygen is more electronegative, nitrogen is less electronegative, so nitrogen is better at stabilizing the positive charge. Right? And remember that stable equals weak. So if the positive charge here is more stable, that means that this is the weaker acid, and then this is the stronger acid. All right, now remember that there's a relationship between the strength of an acid and its conjugate base, or a base and its conjugate acid. The stronger the acid is, the weaker its conjugate base, and vice versa. The weaker the acid is, the stronger its conjugate base. So not only can we use this information about cationic acids to determine the relative strength of two acids, but I can also use it to compare various bases. And so if I want to know which one of these bases is stronger, I can look at its conjugate acid, right? So if I'm thinking about this base, this is its conjugate acid. And for this base, this is its conjugate acid. And so if this is the weaker conjugate acid of the two, that means this is the stronger conjugate base of the two, right? So because this compound has a weaker conjugate acid, it is going to be the stronger base. All right, so when the positive charge in our cationic acids is on different atoms, it's pretty easy. We just use the electronegativity. When the positive charge is on the same atoms, then it's not so easy. And in this case, we're going to look at the conjugate bases. Right? So for example, if they gave me these two acids and asked me which one is stronger, well, the first thing I'd look at is what type of atom is the positive charge on. In this case, the positive charge is on a nitrogen. In this case, the positive charge is on the nitrogen, so the electronegativity of nitrogen won't help me. And so in this case, I want to look at the conjugate bases, right? So the conjugate base of this guy, take away an H plus and we get this. The conjugate base of this guy, take away an H plus and we get this. And so then now what we can look at is whether the lone pair on the nitrogen is localized or delocalized. And remember that delocalized means that that lone pair is participating in resonance. So there's no resonance that this lone pair can participate in. So this lone pair is localized. Now in this compound, this lone pair, we have an allylic lone pair, right? And so we can draw all these resonance structures involving this lone pair. And in many of the resonance structures, the nitrogen doesn't have a lone pair. So what that's telling us is that when the lone pair is delocalized, as it is here, right, if it's not on the nitrogen in a lot of the resonance structures, then in the resonance hybrid, there's going to be less lone pair character on that nitrogen, and so it's not as available to accept a hydrogen, right? And what makes a base is its ability to accept H pluses, so delocalized electrons are less available to accept hydrogen atoms, and that means that they're going to be less basic. So we decided, since this compound is a stronger base, since its lone pair is localized, this base is a weaker base because its lone pair is delocalized, then back to our original question, if this is the stronger base, then this is the weaker acid. And since this is the weaker base, this is the stronger acid. So if the positive charge is on the same atom, check their conjugate bases. A localized lone pair is going to give a stronger base. A delocalized lone pair is going to give a weaker base. Now, if the lone pair in both bases is localized or the lone pair in both bases is delocalized, then we may not be able to answer this question so easily. All right, related to what we were just talking about, the fact that delocalized lone pairs lead to compounds being less basic, amides, which are fairly similar to amines, are actually not very good bases because while they have that lone pair on the nitrogen, it is delocalized. So amides, not great bases. All right, and so one of the most important take-homes from this section is that amines often act as bases. Right? So amines are weak bases in organic chemistry, but while they're weak, they're better bases than many of the other functional groups that we deal with. Right? So here we have a lone pair on a nitrogen, and so if we add an H plus to it, right, if it acts like a base, it's going to accept an H plus, that positive charge will be on a nitrogen, which is pretty good at stabilizing positive charges. So that's what makes amines relatively good bases. But when you look at a lot of the other functional groups that we have, alcohols, ethers, aldehydes and ketones, carboxylic acids, in all of these cases, the positive charge is going to end up on an oxygen atom, which is less good at stabilizing positive charges than nitrogen is. And so all of these will be poorer bases than an amine. And we just talked about amides. They have a lone pair on a nitrogen, and so we end up with a positive charge on a nitrogen, which is pretty good. But as we just discussed, because this lone pair is delocalized, it doesn't make it a very good base. So compared to most of the other functional groups that we deal with in organic chemistry, amines are pretty good bases. All right, so let's finish up with a couple examples. So in this case, I want to identify the stronger acid in each pair. And so I'm comparing first these two, right? Which one of these is stronger? And so these are cationic acids, so I look at the atom with the positive charge, and I've got nitrogen versus oxygen. Since nitrogen is less electronegative, it's better at stabilizing a positive charge, which means, right, stable is weak. So that means that this acid is weaker than this one. So let's use a different color. right? So this is, among the first pair, our stronger acid. Okay, when we go to this next example, so I'm comparing this compound to this one, here the positive charge is on the same atom in both cases, a nitrogen. And so what we do in this case is look at the conjugate base. And so the conjugate base of this first compound would look like that. And I don't see any resonance patterns that that lone pair can participate in. So this has a localized lone pair, whereas the compound, or the conjugate base of the compound on the right, right, we have an example of an allylic lone pair. So I can draw lots of resonance structures. I'm just going to draw the arrows for one of them. Right, and then we continue to move what's going to end up being the lone pair around that benzene ring. So this lone pair is delocalized. And remember that delocalized lone pairs are less basic. Right, so in this compound is more basic. So if this is the stronger base and this is the weaker base, then, right, stronger base, weaker acid, weaker base, stronger acid. So in this case, that is our stronger acid. All right, so one final example. In this case, we're asking the opposite question. So here we have neutral compounds, and we want to know how basic they are. And so if these compounds are bases, then we're looking at their conjugate acids, which are going to be cationic. And so in this case, we'd end up with a positive charge on a nitrogen versus a positive charge on a nitrogen. So what we did in that case to break the tie is we looked at the conjugate base of the acid. So in this case, we're just looking at the bases. And I want to know whether my lone pairs are localized or delocalized. So each of these nitrogens has a lone pair. In the first case, right, that lone pair is delocalized. In this case, that lone pair is too far away from that pi bond, so I don't see any resonance patterns. So in that case, the lone pair is localized. And so localized lone pairs are going to be more basic than delocalized lone pairs, because in a lot of the resonance structures, that lone pair is not even on the nitrogen. So localized lone pair is going to give us a stronger base. All right, and in the last example, I'm comparing this compound with the double bond to the oxygen and the double bond to the nitrogen. So the conjugate acids of these compounds would look like this. And we know that nitrogen is better at stabilizing the positive charge. So more stable conjugate acid. That means the conjugate acid is weaker. And so that means that this is going to be the stronger base.